Hello, welcome to COP 4708. One of the most important issues in a database that's being shared by many users. Some of them can read only, and some of them can read and write. The people that can read only don't present any problem. The people who can read and write must be managed so you will not have two changes or writing at the same time in the same record, which might cause data loss or maybe deletion or missing data. So this chapter actually addresses managing multi-user databases. Whether we have small or large database, this database needs administration, which will include all companies' data assets. The one who administrates might be a single person or a whole office. Their main job will be to facilitate the development and use of the database. Database administrators list certain tasks. Those are the tasks that's been actually done by database administrators. So the first thing that they do is managing the structure of the database to make sure that it does represent the system. Since we have many users, the administrator or administrators or the administrator office task will be to control the concurrent processing of users' requests. Those requests will include those tasks for the administrator will include managing the different rights and responsibilities for those users and assigning for each one the proper security level based on his or her job assignment. So not everybody have the same level of access, not everybody have the same level of authorization to get to the database. Another important task is to back up the database to make sure that they can recover the database in case of any physical or operational failure. Managing also part of their job is managing the platform or database management system that communicates with database, and of course the task of maintaining the data repository. When building the structure of the database, administrators participate in database and application development. They assist in gathering requirements and data model creation. They also assist in database design. They help in the process of changing database structure, seeking best practice solutions, and providing a form to get a feedback results from those changes. Once a change is implemented, problems will happen and administrator should be prepared for what might show up. Once the problem has been solved, the problem and the solution should be documented in addition to the actual documentation of the database structure. That will benefit in future designs or future database problems, which will assist as historical information or historical data. Concurrency control is one of the toughest tasks for database administrator, where they have to ensure that no interference between the work of two users is happening. There is no single technique that can address the issue of concurrency control, and most of the time trade-offs needs to be made between throughputs and the level of protection. In most databases, applications users submit work in the form of transactions or logic unit of work, which is a series of action taken against the database that occurs as an atomic unit. When we say atomic unit here, we mean one unit. So all action has to be completed successfully or none of them will be executed. It will go through that transaction and it will go through the different activities within that transaction. If one of them was not executed properly, then it will cancel the whole unit or the whole logic work unit. This figure shows some of the errors that might happen if not using atomic transaction. Customer made an order. A change was made to increase the amount due. Another change was made to give the salesperson his or her commission, but inserting a new order was never completed. So a customer was billed for an order that was never received. This figure shows the difference when using the atomic transaction, which made sure that either all actions were completed successfully or none will be performed. So if the customer did not receive or the item was not shipped to customer, then the customer will not be billed and the salesperson will not take a commission. The user can see two or more transactions being processed against the database at the same time, which can be called concurrent transactions. But actually the CPU can process one transaction or instruction at a time. The operating system has the ability to alternate CPU services among transactions so that some portion of each transaction is carried out in a given interval. Some of the problems that might appear during concurrency are the loss of data and the inconsistent reading points or reading for the transaction. This figure shows an example of concurrent transaction processing where we have user A trying to read and write item 100 while user B trying to read and write item 200. If we look deep inside the operating system, actually while user A is reading item 100, the CPU will switch to user B. So two users working at the same database will think that they are working simultaneously. Suppose that both users will be working on the item 100. User A going to order 5 and user B will order 3. The CPU will execute the request of reading item 100 from user A, then switch to B while user A is reading. Then go back to user A and subtract 5 units from item 100, which had initially 10 units. The next step will be to set item count as 5 units, then write item 100 for A. But the problem that the initial reading for B was also 10. So when user B subtracted 3 units or 3 items, he or she did not or did it from the 10, and B will set the new counter to 7, which means that the transaction that happened for A setting the count and writing were lost, and the final count will be 7 instead of 2. But how do we solve such a problem? We can do that through what's called resource locking, which can prevent multiple applications from obtaining copies of the same record when the record is about to change. So we lock that item if someone is working on it, and we will not allow anyone else to work on it until it's released by that person or that resource. The locks could be implicit, which can be placed automatically by the database management system, or explicit locks, which could be issued by commands sent to the database management system from the application program. The explicit and implicit locks can be applied on rows, but if we want to apply a lock on a whole table, when we need to know the row, the explicit and implicit locks can be applied on rows. But if we want to apply a lock on a whole table, then we need to know the row, the page, the table, and the database level that need to be locked, which is the size of a locked resource, or what's called lock granularity. Large granularity is easy to manage, but frequently causes conflicts, while small granularity is hard to manage with less conflicts. Locks have two types, either exclusive or shared. When we say exclusive lock, it prohibits other users from reading the locked resource, while shared lock allows other users to read the locked resource, but they cannot update or do any writing. This figure shows an example of concurrent processing with explicit locks. The transactions for one user are grouped together. So in spite of B requesting to read item, it was not processed and was put on hold until all transactions of process A are done. Sometimes we can run two concurrent transactions and generate results as if each one of them ran separately. Those type of transactions are called serializable. To achieve that, we can use two-phase locking technique. In the two-phase locking transactions are allowed to obtain locks as necessary, which is called the growing phase. Once the first lock is released, no other locks can be obtained, and that's called the shrinking phase. Locks can also be obtained throughout the transaction, and no locks is released until being committed or commit or rollback commands being issued, and this is considered a special case of two-phase locking. This strategy is easy to implement but more restrictive than the general two-phase locking. Deadlock is a dead end that the system will reach to when two transactions are each waiting for resources that other transactions are holding. For example, if you have a printer that's been used, or you have you are trying to print a report from the database, or you are trying to write a record, but it was not released by the other users. In this case, you will reach to a dead end. So what would be the solution? We can either prevent deadlocks through allowing users to issue all lock requests at one time, and to require the application programs to lock resources in the same order. Or we can do deadlock avoidance. We can avoid it. For each resource request that can be satisfied, we can determine whether the request should be delayed in order to avoid a possible deadlock in the future or not. So we can study that request and know exactly, we can determine what do we need to do with it, delay it or process it. And if we delay it, we might avoid a possible deadlock. The third one is deadlock detection and recovery. So we can detect a deadlock and then we can recover. We detect the extents of deadlock, and every database management system has algorithm for detecting these deadlocks if they occurred, and the database management system will abort one of the transactions and roll back partially completed work. So if A did not complete all the transaction within it, then it will roll back and go back to 0, as if that transaction or that process or that user did not do anything. This figure shows an example of a deadlock. User A requests a paper while user B requests a pencil. Now user A requests a pencil to write on the paper, but he can't because that resource has been locked by user B, and user B will request a paper, but it has been locked by user A, so every user will be waiting for the other to release the resource that's being held to complete execution. The two processes are in a deadlock. From looking at the deadlocks, we can see that we have optimistic locking and pessimistic locking. The optimistic locking, when we assume that no transaction conflict will occur. And in this case, the database management system processes a transaction, checks whether a conflict occurred, and if not, the transaction is finished. If there is a deadlock, then the transaction is repeated until there is no conflict. For pessimistic locking, it will assume that conflict will occur, and at this point, locks are issued before a transaction is processed, and then the locks are released. Optimistic locking is preferred for the internet and for many intranet applications. In the SQL code, you can see that when the update process needs to be executed, the product is being locked until execution is completed. Once the process is done, the product is unlocked. The check happened before the update, so if there is no conflict, proceed, otherwise repeat until update is successful. In the pessimistic locking, locks will be issued at the beginning of the transaction and released at the end of the transaction. Due to the complication of locks, most application programs do not explicitly declare these locks. Instead, they mark the transaction boundaries such as begin, commit, and rollback transaction, and the application also can declare locking behavior that the database management system should use. The advantages of declaring locking behavior is that in case of any change, only the lock declaration needs to be changed and not the application program. In this code, you can see that the transaction boundaries has been marked with begin transaction, commit transaction, and rollback transaction. Remember in previous slides we talked about atomic transaction, and we said that it means either execute all actions as one unit or none. In this slide we will introduce acid transaction, which are the transaction that is atomic consistent, isolated, and durable. Durable means that committed changes are permanent. So the consistency in this case could be on two different levels, either statement level or transaction level. On the statement level, the rows is being processed consistently, while transaction level, all rows impacted by the SQL statements are protected from changes during the entire transaction. In this level, the transaction may not see its own changes. In the isolation process, the isolation means application programmers that are able to declare the type of isolation level and to have the database management system manage logs so as to achieve that level of isolation. In the SQL 92 standards, 4 transaction isolation levels are defined: the read uncommitted, read committed, repeatable read, and serializable. This table shows the different problems that might happen during transaction isolation, such as dirty read, which occurs when a transaction reads a row that has been changed but not committed. In this case, the transaction that made the dirty read will be processing incorrect data. Non-repeatable reads occur when a transaction rereads data it has previously read and finds modifications or deletions caused by a committed transaction. And phantom reads occur when a transaction rereads data and finds new rows that were inserted by a committed transaction since the prior read. As shown in the table, at least one problem might happen in the first 3 levels, but none of these problems will happen in the serializable level.